This video is going to go over spontaneity, the idea of spontaneous and non-spontaneous reactions, along with Gibbs free energy, changing Gibbs free energy, that's delta G, and entropy, which is abbreviated with a capital S. So we're going to combine delta G and delta S with the previously described parameter change in enthalpy, delta H. And we'll talk about how they combine to determine whether or not a process will occur spontaneously or not. So let's start with sort of what spontaneous means. So if we have this flask, and these two flasks, one side of the flask is filled with a gas, and the other side is completely evacuated, it has nothing in it. And we have a closed stopcock, and so the gas particles are sort of stuck on the left side. If we open that stopcock, then I think we all agree that those gas particles will spontaneously distribute themselves across the two flasks. We also know that the reverse process, the gas particles collecting themselves only on one side of the flask, that is a non-spontaneous reaction, that will not happen unless we put a lot of work into separating them, right? If we have some energy we want to put in, we could try to separate them. So the process shown is a spontaneous process, which means that we don't have to put energy in order to have it occur. It will occur on its own. And that this reverse process is definitely non-spontaneous. This is another example. If we have nitrogen enclosed in a flask on the left and iodine gas enclosed in a flask on the right, and we open that stopcock, we know that these two gases will spontaneously mix together because they will both diffuse across both flasks. Now let's talk about phase changes. So here we have a solid on the left, it looks like ice, and then we have liquid water on the right. And the question is, will the ice on the left spontaneously form the liquid water? Now I think that everyone would agree that if I put a flask of frozen water on the table, on the counter in front of us at room temperature, that it would certainly spontaneously melt. However, if I put it in the freezer, it would not spontaneously melt. The reverse process would be spontaneous. It would freeze. And so some processes, the spontaneity of those processes depends on the temperature. We're going to talk about sometimes why that's true, but that's certainly true for phase changes, that the temperature determines whether or not it is spontaneous. We can also see for the first time here that if a process going forward is spontaneous, the reverse process would be non-spontaneous, but that if you change the temperature, sometimes you can change which direction is spontaneous. So while we're talking about phase changes, I wanted to return to the idea of enthalpy, which remember is abbreviated with a capital H. And we're going to talk about the three different phases and converting between those two of those phases. So you can see enthalpy, capital H, as a vertical scale on the left-hand side of the slide. And what that's supposed to imply is that solids have the lowest enthalpy of the three phases, and that the gas phase has the highest enthalpy, contains the most heat at constant pressure, and then the liquid phase has an intermediate enthalpy value. And so if you want to go from solid to the liquid, that would be melting. That is an endothermic process. And if you want to go from the liquid to the vapor, you have to put heat in. That is also endothermic. And so heat has to go in order to cause these phase changes to occur. And you can see the delta H with the subscript fusion. That is the change in enthalpy required to melt a solid and turn it into the liquid. And delta H with the subscript vape is the delta H, or heat of vaporization, which is the change in enthalpy required to go from the liquid to the gas phase. Now we can also remember phase changes. Also, you can go from the solid straight to the gas phase at certain. Back to this previous slide, heat of vaporization, let's say one of our body's mechanisms for cooling ourselves down is to sweat. And the reason that works is because the liquid that you sweat out, the sweat on your skin, evaporates, and when it evaporates, that is an endothermic process which cools you down. So if we go back here to these delta H values, you can see that they are going to have the same magnitude but opposite sign of the reverse phase change, right? So the heat of deposition is going to be the same magnitude as the heat of sublimation, but it will be negative instead of positive. Now, let's talk about a few other processes that you would have done in the lab where you were trying to identify spontaneous versus non-spontaneous processes and identify where that spontaneity came from. So stretching a rubber band, this is definitely, if you think about if you wanted to take a rubber band that was in its sort of contracted state and pull it apart, stretch it, then that requires energy on your part. And it doesn't just spontaneously stretch out unless you pull it apart, which means that the stretching process is definitely non-spontaneous. But then if you just let it go, it will spontaneously contract back to its original form, unless, of course, you have influenced the integrity of the rubber. But for a normal rubber band, when you let it go, it will spontaneously contract back to its original size. Now, we have we're going to go back to our sort of flask that has one gas on one side and another gas on the other side. When we open the stopcock, we know that these gases will spontaneously mix together if we open the stopcock. And so you can see that here the red and the blue gas particles have distributed themselves equally kind of across the two flasks. Now, the reason why this happens is because at the top what we see, this system represents what's called low entropy. And at the bottom, what we see is a system that has high entropy. And so let's start by talking about entropy. Entropy is abbreviated with a capital S. And entropy is related to sort of the number of ways that we can configure a given system. So it's sort of related to the number of ways we can distribute those gas particles. And the way we generally think about entropy in general chemistry is that entropy is like the amount of disorder in a system. So the more disordered a system is, the higher its entropy. So the top has low entropy because it's more orderly, right? It has, the blue ones are specifically on the left-hand side, the red particles are specifically on the right-hand side. The bottom has higher entropy. There's more randomness in the system at the bottom. So what we can say for sure for this system is that the change in entropy, which is abbreviated delta S, is what drives the process that we see here. That is what causes this process to be spontaneous. So we're going to start using words like something drives something to occur. Okay, that means that for a given process to be spontaneous, it is often driven, quote, driven by change in entropy, delta S, like this one, or it might be driven by the change in enthalpy, delta H, or it could be that both processes, that both delta H and delta S result in a spontaneous process. So we're gonna put them all together in a few minutes. Entropy is related to the second law of thermodynamics, so I'm not sure we've actually stated all the laws yet. The first law of thermodynamics states that energy can neither be created nor destroyed. It is only converted from one form into another. The second law of thermodynamics deals with entropy, and so the second law states that various ways, but one way of saying it is that the entropy of the universe is always increasing. And so the entropy tends to stay the same or increase in a given system. So systems are driven to higher entropy. That is sort of their preferred favorable direction. And most people like to give the scenario that your dorm room tends to go to a disordered state on its own, and that it takes a lot of energy to clean it back up again, right? So the moving to the disordered state or higher entropy state is the spontaneous way that it wants to go, right? The way that it tends toward. Now I just like this cartoon, Entropy Seminar, the results of a 5-year study into the second law of thermodynamics, and it's inevitable, and then it kind of all falls apart, right? So that's sort of a, you know, disorderly words, right? So we're increasing the entropy as we go down. Thought it was funny. Anyway, so now we can predict the sign of delta S for certain processes, and so we've already looked at this one. Mixing two components together to form a mixture. Because the top is lower entropy and the bottom is higher entropy, we can definitively say that this process, going from the separated gases to the mixed gases, this process of mixing has an increasing entropy associated with it. So we would say entropy is increasing, and we would say that the delta S of this process as it's drawn is positive. Now, if we reverse this process, and we change that arrow in the other direction, we'd say we're going to separate the two, then the relative entropy of these two states, is still the one on top is still lower entropy, but that's not the product, right? And so we can say that the separation, going in the opposite direction, is definitely decreasing, and that delta S would be negative. So delta S, like delta H, is a state function, and therefore the value of delta S only depends on the initial and the final states. And so one thing that's true about delta H that is also true about delta S is that if you reverse the reaction or the process, then the reversed process has a delta S value with the same magnitude or absolute value, but the opposite sign. Okay, so let's keep going and talk about processes. Phase changes we talked about in terms of enthalpy, but let's talk about their entropy. So you can see the images of ice and liquid water and steam, and then you can see if you put on your molecule glasses what those sort of molecular view of ice and liquid water and gaseous water would look like. And so you can see that the water, the solid on the left is highly ordered, right? Those molecules tend to stay in their position. As opposed to on the far right, those gas particles are moving around very quickly and have a high state of entropy. And in the middle, it's sort of an intermediate state of entropy where the liquid molecules tend to move past each other, but they are not as disordered as the gas particles on the right. So the left has the lowest entropy, the solid phase, and the gas phase has the highest entropy, and the liquid phase is intermediate. And so that means that if you're doing a phase change from left to right here, that entropy is definitely increasing, which means that delta S would be positive. However, we all know that phase changes can go in the opposite direction. So just like delta H before, if you're going from, instead of going from the solid to the liquid to the gas, if you're going from the gas to the liquid to the solid, or any combination of that, that would have the opposite sign of delta S, and entropy would be decreasing in that case. We're going to do some practice problems later to hopefully that'll make sense. Another kind of reaction where you can predict the sign of delta S is because gas particles have high entropy. If a reaction involves changing the number of gas molecules present, or gas particles, whether they're molecules or atoms or whatever, if the number of gas particles changes during the course of a reaction, that will change the entropy of the system. And so on the left-hand side, we have a lower entropy system because we only have 5 particles of gas. On the right-hand side, we have converted those particles of gas into, we've doubled them, right? So we've converted each molecule of N2O4 into 2 molecules of NO2, which means we have twice as many gas particles on the right-hand side. So on the right has higher entropy than the left. And so we know for sure that entropy is increasing as we go from N2O4 to 2NO2. And you can tell that just from the stoichiometric coefficients. There's 1 mole of N2O4 and 2 moles of NO2. If they're both in the gas phase, then you would definitely say that delta S is positive for that reaction. And then if we're going in the opposite direction, you would say that entropy is decreasing and that the sign of delta S is definitely negative. Now, dissolving a solute into a solvent. So what you see here is sodium chloride, and we're dissolving that in water. Now it doesn't have to be a salt, it doesn't even have to be a solid solute that you're dissolving. Anytime you dissolve something and form a solution, the solution has higher entropy than the separated solute and solvent. And so entropy is definitely increasing as you go from the separated solute and solvent on the left to the aqueous or whatever solution on the right. So delta S would be positive for any dissolution process. In a previous lab, we also looked at precipitation reactions, and we described a precipitation reaction as being the opposite of a dissolution, which is true, which means that if you're performing a precipitation reaction, you know that delta S will be negative, right? Because it's the opposite of a dissolution. Okay, so just to summarize the different types of processes where we can predict the sign of delta S. We talked about phase changes. That's a solid going to a gas. And you know that the solid has the lowest amount of entropy and the gas has the highest entropy. So if you're going from the solid to the liquid or the liquid to the gas, entropy is going up. If you're going the opposite direction, entropy will be going down. In a dissolution process, delta S is definitely positive. When you change the number of molecules of gas, so for example here we have 2 moles of NO2 or 2 molecules of NO2 on the left, and we're forming 2 molecules of nitric oxide plus 1 molecule of oxygen. So that means we have 3 total molecules on the right of gas. And so that means we're going from 2 moles of gas to 3 moles of gas. So the sign of that particular process for delta S would be positive. And the reverse process, going from 3 molecules to 2, would be negative. And when you mix components together, here we have 2 gases that we're mixing, but it could also be 2 liquids, whatever. Whenever you have separated components and you mix them together, then you definitely end up with a higher entropy state in the mixture. Now, this idea here, this is a table in your textbook, and here we're putting concepts together. So here we have delta H and delta S. And so we've talked about change in enthalpy and change in entropy. Delta G is the change in Gibbs free energy, and that is actually the quantity that determines whether or not a process is spontaneous or not. So when delta G is negative, then you know the process will be spontaneous. When delta G is positive, the process is definitely non-spontaneous. And so you can see the equation here, delta G equals delta H minus T delta S. That equation can be used, and I think that one's on your equation sheet. That equation can be used to determine the overall sign of delta G, and that can be used to help you figure out if a process is spontaneous or not. So we're going to look at sort of this region of the table, and we're going to try to rationalize all of these things. And we're going to start with a mathematical rationalization, and then we're going to talk about it more scientifically, conceptually, using chemistry. So let's start with a mathematical description. So I just expanded that graph, that table. And so I want to talk about this equation, delta G equals delta H minus T delta S. We're going to start with the situation at the top where you have a negative delta H and a positive delta S. Okay. Now, if you have a positive delta S, then this part here, this negative T delta S, that means we're subtracting a positive value from a negative value. And so if we're subtracting something from something that's already negative, then this will always, the result, delta G, will always be negative. You cannot get a positive value out of that. So when delta H is negative and delta S is positive, delta G will always be negative, which means that that will always be spontaneous. You can see the result in spontaneity on the right-hand side. We're going to talk about that in a few minutes. Now let's change things a little bit. Make this positive delta H and a negative delta S. Now what we're doing is we're subtracting a negative value, which is like we're adding a positive value. So we're basically taking a positive number and adding another positive number to it, which means that delta G, the result of this mathematical equation, will always be positive, which means it will always be non-spontaneous. Now things get a little bit more confusing mathematically when we have delta H and delta S being the same sign, them both being negative. Now, if you look here, we're still subtracting a negative, which means we're adding a positive value, but we're adding a positive value to a negative delta H value. So that means that delta H is some negative value. If we add a number that's large enough, we will make a positive number. But if what we're adding is not large enough, it will stay negative, right? So I don't know if that makes sense to you. But what that means is that the size of this T value, the size of the temperature, is all of a sudden very, very important. Okay? And so what that means, in other words, if the temperature is a really, really big number, that means that all of a sudden this T delta S term is going to be really large. So then we're adding a really big number to a not as large negative number, and it's more likely that we'll get a positive value out of it. On the other hand, if T is really small, that means that that T delta S value is not very big, and so that means that even though we're adding something positive, we can't quite get a large enough number to make it a positive delta G overall. It'll just stay negative because of delta H, right? So if we summarize these results, then delta G, the product of the result of this calculation, will be negative when T is a small value, when the temperature is low. And it'll be positive when T is large. Okay, when T is large enough, then the addition of that positive T delta S will all of a sudden become very important, and it'll overcome the negative delta H and make a positive delta G. So if you put in numbers there, I think you can eventually rationalize what that means there. Now, on the other hand, do one final example where they're both positive. So if they're both positive, that means that again, you're subtracting a positive value, but you're subtracting it from a positive delta H value. So eventually, if you subtract a large enough T delta S value, then that result will become a negative number, right? So that means that the size of T is still important. The size or magnitude of the temperature is very important. So the result, delta G, will be negative when the temperature is large. So you're subtracting a really big value. And it'll stay positive when the temperature is small, because you start with a positive delta H and you're subtracting a number, but it's not nearly as big as delta H started as. So we can also rationalize this conceptually, and you can kind of rationalize it however you want, but you do need to be able to sort of answer questions that relate to these values, and we'll practice some of this in a few minutes. So we can rationalize all of this conceptually as well. And so conceptually, I want you to think about a negative delta H. When we learned about negative delta H, what we learned is that that is an exothermic process. And I want you to think about an exothermic process. Remember, that's where heat is released. We have extra enthalpy at the end. We release that heat to the surroundings. Those reactions, those processes are much more likely to result in a spontaneous reaction than not. And so what that means is that a negative delta H or an exothermic process, we would think about that as a favorable kind of situation. And we also learned that the second law of thermodynamics states that the entropy of the system, the entropy of the universe is always increasing. And so the system really wants to have higher entropy. It tends toward higher entropy. And so what that means is that a delta S that is positive when entropy is increasing, that is a favorable situation for the system. So if you put together a favorable delta H and a favorable delta S, that means that this process will definitely be spontaneous under all conditions. Now, if an exothermic reaction is favorable, then an endothermic reaction with a positive delta H must be unfavorable, meaning it's less likely to produce a spontaneous process. Decreasing entropy is unfavorable. So when you put two unfavorable parameters together, you're going to get a non-spontaneous process no matter what you do, because nothing is favorable. The outcome does not look good. Now, when we combine a favorable delta H with an unfavorable delta S, then what we see again is that the magnitude of the temperature is important. So think about the temperature as determining how important the delta S term is. So what I mean by that is if you see, for example, what we're looking at now where they're both negative, you see that delta H is favorable and that delta S is unfavorable. So what that means is that this reaction will be spontaneous, which means if that's true, it's spontaneous whenever the delta H value has 1, right? The favorable parameter has 1 in this case. And that's going to be only at low temperature, because at low temperature, delta S is not very important, because you multiply T times delta S and that sort of magnifies it, right? And so how big the temperature is determines how big delta S is magnified. So at low temperature, delta S is a very unimportant term, and delta H wins, and therefore since delta H says that it's favorable, it's going to be spontaneous. Now, once T gets to be large, this process would be non-spontaneous, because at a high temperature, delta S wins, because at high temperature is where delta S becomes more important. Now at the bottom we have an unfavorable delta H and a favorable delta S, but you still think about temperature as determining when delta S wins at high temperature or when delta H wins at low temperature. So we would say that this is spontaneous when delta S wins, at high temperature, because delta S is the favorable term here. And it is non-spontaneous when delta H wins, because delta H says that it's unfavorable. And so at low temperature, delta S is not important enough, and then delta H will sort of supersede that. So make sure this makes sense. We can expand out to the rest of the table so that you can see examples of these reactions. And we'll do some examples as practice problems. Speaking of practice problems, we're going to do these next. A particular process has a delta H of negative 4.6 kilojoules per mole and delta S of negative 16.9 joules per mole Kelvin. Calculate delta G in kilojoules per mole at 45 degrees and determine if the process is spontaneous at this temperature. So we have negative 4.6 kilojoules per mole. We're going to convert 45 degrees Celsius into Kelvin to get 318.15 Kelvin. Then delta S, we're going to plug in here next to temperature. But one thing you need to know is that delta H, you'll notice, is in kilojoules per mole. We're supposed to calculate delta G in kilojoules per mole. Delta S is in joules per mole Kelvin, so we need to convert that into kilojoules per mole Kelvin. So we're going to move the decimal over 3 to get kilojoules per mole Kelvin. So that's a negative 0.0169 kilojoules per mole Kelvin. And the kelvins cancel, and then you end up with two compatible units, kilojoules per mole. So negative 4.6 plus 5.3767 plus, it seems, oh, okay, yeah, all right. Sorry, I multiplied by 318. I forgot about that temperature in there. I thought I made a mistake. So we're going to add those two together. Negative 4.6 plus 5.3767 is going to give me a pretty small number, 0.7767. That number is positive, which means it is non-spontaneous, because anytime you get a positive delta G, that's true. We're going to round to the right number of significant figures. It appears that we just need one sig fig, and that's because delta H is only accurate to the 10th place, and we're adding in T delta S, which is accurate to the 100th place. So when we add those two together, we get a number that's only accurate to the 10th place, so 0.8 kilojoules per mole. Now, number 2, part A. Consider the processes below. Identify the signs of delta H, delta G, and delta S if possible. For any that are not determinable, with the information provided, write in D. The following delta H values might be helpful. So we have heat of formation values for gaseous, water, and ozone gas. Okay, so dissolution of calcium chloride causes the test tube to get hot. So that is an exothermic reaction. You know delta H is negative. We're dissolving calcium chloride, and we talked about the fact that whenever you're dissolving a solute in a solvent, that the delta S value is definitely positive. So we know that's true. Now, when you put these two together, a negative delta H and a positive delta S means that you will always have a negative delta G. There's no other way of combining those two to not get a negative delta G. We talked about that too. The following reaction is spontaneous. Sodium bicarbonate, HCl, forms CO2, water, and sodium chloride. So we know it's spontaneous, which means we know the sign of delta G is negative. The only other thing we can see in this problem is we can see that we go from 0 moles of gas on the left to 1 mole of gas on the right, which means that because we form a mole of gas that was not there before, then delta S is positive. Now, with a negative delta G and a positive delta S, you can't make any conclusions about the sign of delta H. We don't really have enough information to figure delta H out, so you would write that delta H is not determinable. Formation of water vapor is part C. So we're forming water vapor from oxygen and hydrogen. Here, we know that we can count the number of gas particles, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 particles of gas on the left, 4, 5, 6, 7, 8, 9, and we have 1, 2, 3, 4, 5, 6 moles of gas on the right. So we're decreasing moles of gas, which means delta S must be negative. Now, one thing that I only notice now that I reread this question is that we're given the fact that the heat of formation of water vapor, which is what we're doing here, we're forming water vapor from its elements, is given at the top, and it is a negative value. So that means that this must be an exothermic reaction as we have written it. So I wrote not determinable delta H, but that's not true. I'm now rereading this and I see that delta H is actually negative because I'm given the heat of formation of water vapor, which is exactly what this reaction is describing. So delta H is negative, in fact, in this problem, part C. Now, if delta S is negative and delta H is also negative, you cannot determine delta G. You don't know if it's spontaneous or not because one of them is favorable and the other one is unfavorable. So it depends on the temperature. If we move on, to part D, we're converting ozone to oxygen. We have 1, 2, 3, 4, 5, 6 molecules of ozone. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules of oxygen, which means we're going from 6 moles of gas to 9 moles of gas, which means delta S is definitely positive. We also, I didn't read this at the top, the heat of formation of ozone, which is the opposite of what this reaction is describing. This is ozone being converted into oxygen. So if the heat of formation of ozone is 142.3, it's a positive value, that means the reaction that's written here must be negative. And so it must be exothermic. So delta H is negative here, even though I'm going to write on here that it's not determinable. That's actually not true. Because I know the heat of formation of ozone is positive, I know that this reaction, the way it's written, which is the opposite reaction, is definitely negative. So delta H is definitely negative. If you combine a positive delta S and a negative delta H, then delta G also has to be negative. And so delta G and delta H are both negative here, even though I wrote not determinable, that's not true. I forgot about this information that was given up here. Now we have a solid being converted into a gas. And I just know that based on the picture that you see at the bottom, right? So this is a molecular view of a solid, and now these particles are all separated separately from each other. That's the way your book describes the look of a of a gas. So a solid going to a gas, we know that delta S is definitely positive. We also know that the delta H sign is definitely endothermic. Delta G would be not determinable. It would be dependent on the temperature because you have a positive favorable delta S and a positive unfavorable delta H, which means that delta G, it's hard to determine if it is, or it's impossible to determine if that is a spontaneous reaction or not. In the last set, F, we have a gas being converted into a liquid. And so in this case, it's a similar situation, except sort of the opposite. The gas, this has a negative delta S, and it has a negative delta H, and a correspondingly not determinable delta G, as before. And that's because delta S is negative, which is unfavorable. Delta H is negative, which is favorable, so it's going to depend on the temperature and the actual values of delta H and delta S. You have to plug them into the equation like we did for number 1 up there and figure out the actual value of delta G.